of the Gauss application. You know very well, we will discuss about the electric field intensity due to the charged sphere, and it is just similar to the sphere as well as the shell both. Why? Because you know very well, in the cell, at the surface of the cell as well as the surface of the sphere, charge must be retained at the outer side of it. If it is a cell or it is a sphere, doesn't matter, both derivation must be same. You know very well, charge will always resides at the outer surface of the cell or sphere. So we are assuming here capital Q is the charge and R is the radius. If it is given in the question, then we will solve, and if it is not given in the question, we will assume. You know very well, suppose given that surface charge density, not charge is given, but surface charge density of the sphere is given here or cell is given here. So sigma is known as the surface charge density as the previous article we was discussing. And the condition is here, you know, surface charge density, R is the distance of the point P from the surface at which electric field intensity can be calculated. Here P is the point at which we want to calculate the electric field due to that particular large sphere. In Coulomb, we can calculate electric field only due to the point charge, but it is measurable charge. It is not a point charge, and with the help of Gauss, we can calculate the electric field intensity with the help of spherical measurable charge. You know. Similarly, simply we can assume here Q is the charge and R is the radius, and dA is the small surface area assumed at the surface, Gaussian surface. So I am assuming here, what is the Gaussian surface? It is the spherical, because it is a sphere. Now we can use a particular spherical surface instead of a cylinder. Here we will use spherical Gaussian surface. And suppose it is a dA is the small area at this one particular point P, where we want to find the electric field, dA vector will be directed outward, as well as electric field intensity will also be outward due to that particular charged sphere. And you know very well, angle theta between them will be 0. Okay, so now that particular Gaussian surface is given here, and we will find the small flux passing through that particular dA area. Therefore, total flux through the Gaussian surface is given as the, first of all we will find the small flux, and d phi equals to E dot dA equals to E dA cos theta, and since theta is the 0 here, so we will find it E into dA. And similarly, what should be the total flux? Total flux phi E written as the integration. Here it is a closed surface area, so we will use the cyclic integration, closed integration. You know very well, it is symbol of the closed integration, and you know it will be the circular surface, you know, from spherical surface, you know, from 0 to 4 pi r square. 0 to 4 pi r square, and we will find the integration result, and it becomes equation number first. And now you know very well, according to Gauss theorem, total flux about any Gaussian surface will be equal to the 1 upon epsilon naught times of the total charge enclosed by that Gaussian surface. Here charge enclosed is Q, which was spread at the surface of the sphere. So according to Gauss theorem, total flux becomes 1 upon epsilon naught times of the total charge enclosed. Therefore, by equation number first as well as equation number second, we get the result. You know, we get the result, and it becomes E 4 pi r square, choosing from here, and is equals to 1 upon epsilon naught times of the Q. Therefore, E equals to 1 upon 4 pi epsilon naught Q by r square. It is the similar formula like electric field due to a point charge. You know, similarly we can find the result, but it is for the measurable charge, and since it will provide the result of the similar to the Coulomb. Why? Because with respect to the Gaussian surface, that particular charge is treating as a point charge. Gaussian surface will be of any shape and size. You know, E equals to 1 upon 4 pi epsilon naught Q r square by r square. I am multiplying and dividing here so that we can write it. It is a surface area of the sphere. Therefore, we can write at the final, if charge is not given, surface charge density is given, then sigma upon epsilon naught times of the r square divided by small r square, and that particular electric field is at the outside of the sphere. Okay.